So these are the kinds of questions that, depending on how your brain works, you might prefer this type of question because you're like, good, I don't have to do any calculations or think about numbers here. Or maybe if you like thinking about numbers, then this is a question you don't really like. But it is a conceptual one. They're asking about sampling, just the idea of sampling people or objects. And if we run through it, careful analysis of a given sample will indicate whether or not it is random. And unfortunately, we can't know that when we're just looking at the sample itself. All right, if we can see the methodology of getting that sample, then yes, but just the sample itself will not give us that information. It is not A. And that's why if you have a bad sampling method, we're not going to really necessarily know that it was bad data if all we see are the numbers. Sampling error implies an error, possibly a very small, but still an error on the part of the surveyor. No. And we talked about this, so hopefully this kind of sinks in. Actually, no one answered B. So no one thought that. Sampling error is a natural thing, and the surveyor might do everything, well, probably will do everything 100% right and still end up with it. So that's good. No one answered that. Data obtained when conducting a census are always more accurate than data obtained from a sample, no matter how careful the design of the sample. Not necessarily true. We've talked about the limitations of censuses, and one of the big limitations is that that's a lot of data to collect, and opinions can change, and if you miss certain data, then it gives you this false sense of being accurate when it's really not. The clusters in cluster sampling all should look pretty much alike. That is true. Clusters should look alike. Strata in stratified samples should be separated based on certain variables, certain characteristics. And finally, the sampling frame is the population of interest. It's going to be close, but the sampling frame is the actual people you can draw your sample from, which does not always match the population of interest. So very good on that. And if you didn't get it right, hopefully you see maybe where the flaw in your thinking was. All right, we're going to look at the next part of chapter 16. We're going to be, I think we wrap up chapter 16 with this. This is going to be looking at, well, these concepts. You can see it right here. When you're basically transforming a random variable, that's what we're going to be looking at the last part. In the first part, we're just going to be investigating the standard deviation and variance, which there's a lot of words that almost mean the same, that look like they should be this, interchangeable, but variance is a special thing here, and we'll talk about that. Hey, it's camping time again. All right. So remember that campground that we were going to go and camp at, and they had 10 they have 4. Okay, now we're doing a different campsite. I'm sorry. We're going to go camping at I cannot talk. The next 10 weekends, we're going to go to the same campground. There are 10 campsites. We're going to be randomly assigned to a campsite each weekend. We're going to run a simulation to determine how many of the different campsites you will stay in over the following 10 weeks. So let me see. How are we going to set up this simulation? Any thoughts on this? Making you think back to your simulations and how we do that. I do want to remind you that we have a random number generator in our calculators, so maybe that can be a starting point. So we can set up our random simulation, and it will look like this on your calculator when you get to that point. Random integer 1 to 10, so we're saying, like I said, pick some random number between 1 and 10, and now do that 10 times in a row, and it's okay if we repeat. In fact, when you do that, you're going to see some repeat numbers. So when I look at this, the numbers I got, I'll just put them down real quick. I got 4, 8, 7, 2, 10, 3, 8. You're gonna have to scroll to the right to see all of them. And I got 2, 7, and 1. So if I think through how many different campsites did I stay at? I stayed at 1, 2, 3, 4. I didn't stay at 5 or 6. I stayed at 7, 8. I never stayed at 9, and then 10. So I stayed at 1, 2, 3, 4, 5, 6, 7 different campsites right there. Now you got different numbers than I did. So I want you to figure out which or how many of the different campsites you stayed at. And I want you to run the simulation a few times. Luckily, all you have to do at this point is just keep hitting enter. And it'll give you a new set of 10 random numbers. All right, so if we're good with that, let's go ahead and plot the results. So I got 7 on the first one. I'm going to put a dot there. I'm going to run this again so we can get some more data. And I'll let you guys add your dots as you collect that data. Any questions on this?
So we're just putting in every one that we got from the 10 numbers?
You're gonna count how many unique campsites you stayed at out of 10, and then you will record just that number. So you're gonna get
okay.
Yeah. All right, so we've got enough data that now we can kind of come up with a probability distribution based on this. Let me see. We're going to create a probability model for this simulation. All right. Let's see here. We technically have, let me see something. Okay, sorry, I forgot how to set it up. A probability model, we technically stayed at we have 1, 2, 3, 4, 5, 6, to 10. Those are all of our options. And I could say, here are my outcomes. Here's the probability of those. Now I'm going to simplify it a little bit because we didn't stay at 1, 2, 3, 9, or 10. So those are going to be a probability of 0 for all of them, right? Based on our outcomes. Now, if we had done this a million times, we'd eventually get some of that. But with our outcomes, let's simplify a bit. All right, so here's what I'm going to do. If I can erase that. And you can kind of keep track of this on a piece of paper nearby, just so it helps it to make sense for you. So I'm going to do my outcomes that matter here. Is we've got 4, 5, 6, 7, and 8. Those are the only outcomes we actually had any probability of happening. So the probability of those, well, now we have to count our dots, and maybe you guys already did. I counted 26. Let me see, there's 3 here, 2 here. See 9 there, 9 there, and 3 here. So is that looking good? 26? All right. So now we've got our probability distribution. These outcomes is going to be 3 and 26, 2 out of 26, and then 9 out of 26, 9 out of 26, and 3 out of 26. All right. So we're good with that? I hope so. If I'm going too fast, if it's not making sense, then jump in at any point to tell me to slow down. We figured out how to find expected value yesterday, so let's do that now. Remember to, just as a reminder, put this information in lists and let your calculator do the work for you. And in case anyone didn't hear, if you are already finding the next values, which is the distance from the mean squared, you can go ahead and plug those numbers in. I'm going to let you guys fill in the table for that. There it is. So we can see that, let me get going again. Oh no, this video might have been screwed up. I think I was recording when I was meant to pause and pausing when I meant to record. Well, if you need to come back to this video, you might be a little bit confused, and there's gonna be a lot of nothing going on. Okay, so we are looking at these numbers, so it's pretty straightforward. All the negatives cancel out. We're good with this. The probabilities, again, you might have forgotten these, like what the numbers broke down to, but this was 3 out of 26. Is 2 out of 26. This was 9 out of 26, 9 out of 26, and 3 out of 26. So those are the probabilities of those. We've already seen that. What we're going to do is we're going to actually multiply the distance squared multiplied by the probability, and that's going to give us our last column. So now I will pause for real, and you guys can put in the weighted distance. So you can see with this much work, it is really not fun to find the standard deviation. And we're not done yet. Now what we need to do is add all this up, and we'll just do this really quickly. So 0.61 plus 0.13 plus 0.03 plus 0.17 plus 0.33. Oh my gosh, I did all that without actually being in the right spot on my calculator. So let's try it again this time. And you guys are already getting it. So 1.27. All right, and let's take that over to here. We'll look at the next slide. So we're essentially finding the standard deviation by hand, and this is the formula for it. And let me get rid of all of our writing here. Actually, I'll just clear everything and then I'll put that 1.27 back on there. So we got 1.27 when we added everything. And what does that correspond to? That is the sum of everything here. What we did is we took the data point minus the mean, the expected value. That was the very first thing we did. And then we squared it. And then we multiplied it by the probability of getting that particular outcome. So that led to our last column. And then at the end of that, we summed everything up. And when we summed it all up, we got 1.27. So now the standard deviation, is going to be the square root of that. So if I took the square root of this, so 1.27, the square root that is of 1.27, I get 1.127. All right. That's a lot of work just to get a simple number that our calculator can get for us. And some of you are already familiar with that. And we're going to look at that in just a second. But 1.127 is the standard deviation for this data set. And variance is mathematically defined as the square of the standard deviation. And there's no, so before we took the square root of this, it was 1.27. So the standard deviation is this. Variance we just show as standard deviation squared. So my variance is 1.27. the standard deviation is 1.127. We already understand standard deviation, which is kind of the average distance a point is going to be away from the mean. Now for variance, it's a little different. I don't know of a good way of putting it into terms to make it make sense, except it's the total amount of variation in the data. And when we look at this tomorrow, and I think it's, or sorry, not tomorrow, Monday. When we look at this on Monday, we're going to be working with variance more, and that's going to be an important thing to understand. Let's just say that's good enough for right now. So the variance is just going to be the exact same formula I showed you, but without the square root. So nothing has changed here. So lots of stuff going on. And now it's really easy. Actually, let's not even worry about this scenario just yet, though we can plug that in a second just to get more practice. Let's go back to those lists that you already created in your calculator. So without changing anything, I want you to run that one variable stat again. All right, so stat, calc, one variable stats with your frequency list for list 2. Okay, and notice we did some rounding here, but notice that your standard deviation is shown. It's the second to last number there. And what your calculator is showing is the standard deviation here is going to be 1.129. With our rounding, we got 1.127. So I think we can all agree, let's not do that by hand ever again. Okay, but I think it's worth going through one time just to understand where the number comes from. All right. So let me see. I want to see if it's even worth our time. No, okay, I do want to do this. So create these lists. You can overwrite the old lists. We don't care about that data anymore. So if you go and create your lists right here, I have, the outcomes and the probability. So I'll just give you a second to do that. You can go ahead and run your one variable stats again to get your information on them. We will want to have this data. And once you have done your one variable stats for this, feel free to write in, oh, you're already doing it, good. Yeah, write in the values that you find. So that might seem weird to have a mean or expected value of pretty close to 0, and then a standard deviation much bigger than that. But keep in mind, we can have negative values as part of our outcomes here. We can have positive values, and this is not necessarily an unusual thing. All right. So we're going to learn a little bit more about transforming our data. In fact, what we're going to start off with is the idea of adding or subtracting a constant. So luckily you won't need to remember these numbers. Well, I'll just leave them up on the screen. So negative 0.55 and 13.49. That's where we started at. So now we're going to assume all outcomes increase by 5. So what are the new outcomes? And you can just shout them out, or you can write them in, your call. In fact, why don't you guys just write down in the table what the new outcomes are if every one of them increases by 5. So nothing super tricky with what we just did here. Every outcome went up by 5, but plug this new list in, and maybe you want to overwrite the old one, but maybe you just want to create a new list, and that's not a big deal. So we can plug these numbers in. I'll just do it in list 3. So negative 2.5, 10, 15, 30, and 105. Now, and it might be good practice to plug this into a new list. Now, whenever you go into your one variable stats, make sure you're changing your original list to list 3. That's where I put mine, list 3. And my frequency hasn't changed. That's still list 2. And now let's go ahead and add the new expected value and standard deviation for this. All right. That's what I got as well. Hopefully when you guys were plugging this into your calculator, doing the same thing, you found 4.45 for the mean, 13.49 for the standard deviation. So it's a pretty simple question. What changes happened?
The expected value.
The expected value. And by how much did the expected value change?
By 5.
By 5, exactly. So I essentially just took this and added 5 to it. And this standard deviation, we can see no change at all. All right. So this leads us to an understanding about, oh, we're not getting to our understanding yet. I forgot the order I put this in. So we have a pretty good idea of what that means. When we add and subtract a constant, we'll come back to this, our mean changes by that amount. Our standard deviation does not. It's because the spread around that point is the same. It's just taking kind of this distribution and shifting it. But the spread itself hasn't changed at all. So let me go ahead, not clear everything. I want to be careful what I clear here. All right. So I'm going to get rid of all this and that. And there we go. So now let's look at the next one. Now we're going to be multiplying or dividing by a constant. Now imagine that all outcomes double. So your winnings can increase, but so do your losses. All right, so we can fill in this table with our new outcomes. So at this point, we've got our new data set. You might want to create a new list. You can overwrite an old one. But yeah, same thing as before. Plug in this new data and see what happens to your mean and your standard deviation. I'll just leave that there. You guys can fill in those two numbers whenever you are done. So the essential question, assuming everyone's had time to confirm this on their own, the essential question is basically, how is this changing? How does our mean and how does our standard deviation change when we multiply by a constant?
They both double.
They both doubled. We went from negative 0.55 to negative 1.1. That's double. And then it's pretty easy to see the doubling with the standard deviation. So in this case, and we already looked at this before with transforming the normal distribution. So if you think of this just as a distribution right now, by adding and subtracting, we're just moving this left or right. All right, no big deal. But the spread stays the same. When we multiply, we're doing the same thing, but now we might shift the data, but then we might also transform it by re-expressing it. And did we have another word for that? But basically, we want to multiply, and this changes the spread. So now my spread looks like this instead of the original one. So essentially, that's what we're doing here. And there we go. So our takeaway on this is this right here. Let me actually go back one before we focus on that. So the expected value, remember that's the expected value plus a constant. So any outcome, this x represents the random variable. So the random variable plus a constant is just going to be the original mean plus or minus that constant. Now, when we have the standard deviation, if you add or subtract a constant, that doesn't change at all. The expected value when you multiply is to multiply the mean by it. So every single outcome was multiplied by 2 in our example. So we just take 2 times the expected value. Pretty straightforward. So now with these, remember that your variance is your standard deviation squared. So if I'm going to look at that, then the variance of X, and then, well, in here, I mean, they already kind of show it, but it's plus or minus C. So the variance in this case actually doesn't change. So the variance of plus or minus C is the same as just the variance of the original random variable. But when we multiply, remember, this is actually just kind of an algebra thing. When I square this and I bring this out, this is the standard deviation squared. So if I bring that out, then it's actually A squared. So it's kind of a weird thing. And this will come up in your homework. It's going to be a weird idea, but you have this formula you can refer back to. So if you have the variance, or if the random variable is being multiplied by a constant, then the variance is going to be multiplied by the square of that constant. Now, the standard deviation itself is just multiplied by the constant, whatever that is. I was using C right here, but they use A as some examples also. Okay. Anyways, that was just me kind of going through, but that's in the presentation if you want to see it. I will tell you this. There is something kind of tricky with this, and maybe it's best to, okay. How do we want to do this? There's a difference. Let me just tell you this right off the bat, because you might even skip your homework for today. You will, okay, how do I say this? You will come across, if you do this homework right now, your initial thought might lead you to the wrong answer. And you'll be a little bit confused about it. So I don't want you to not try it, but I'm going to give some clarification on problems like this on Monday. Yeah, we have school on Monday. So on Monday, I'm going to go through some problems like this. So let's just, for right now, I will say, try these problems that I assign you. And if they work out for you and you get exactly what you expect, that's great. So in a problem like this, where it's 2y times 20, you know, what you might think is 2 times a random variable y plus 20. Now we know that the mean is affected by both of those. So 2 times 12 plus 20, that's going to change by that amount, okay? Because I just took this formula and substituted in the mean. So the expected value of 2 times y plus 20 is going to be 2 times 12 plus 20. So if you're with me on that, you'll get, 24 plus 20, and you get 44. And if you check the back of the book, that will be correct. Where the back of the book might not come out right for you is with the standard deviation. And I'll talk about why that's the case. Because what you just learned is if you multiply by a constant, then your standard deviation of 2y plus 20, well, adding and subtracting doesn't do anything to your standard deviation. So we actually don't care about that. It's just going to be 2 times the standard deviation of y. So it's going to be 2 times, I'll just write it this way, standard deviation of y, and that is 2 times 3, which is 6. You will probably find a different answer at the back of the book. Again, for right now, don't worry about that. I will clarify that on Monday. But do you guys have questions about what I just did there? I can pause and we can go through that. Okay. If you want to see other examples, just hang out after class and we can do that too. All right. Let me see how many problems we have. Okay. There we go. Okay, so it's kind of like just kind of straightforward as far as these go. Your company bids for 2 contracts. You believe the probability that you get contract number 1 is 0.8 if you get contract number 1, the probability you get contract number 2 will be 0.2. But if you don't get it, the probability of getting number 2 is 0.3. Are the two contracts independent? Let me say it this way. Does the probability of getting contract number 2 depend on whether or not you get contract number 1? Then you can give thumbs up or say yes or whatever you want. All right, so 1 thumbs up here. All right, one way of talking about independence is that the probability of A, actually, let me write it this way. The probability of A given B is equal to the probability of A given not B. So if we get contract number 1, the probability of getting contract number 2 is 0.2. If we don't get contract number 1, the probability that we get contract 2 is 0.3. These are not equal. These are not independent. So now it asks us to find some probability. This is going to be a little bit of review here. So my question is, what kind of diagram do I need to create for this?
Tree diagram.
Tree diagram. All right, when you're looking at conditional probability, it needs to be a tree diagram. All right, we either get contract 1 or we don't get contract 1. I'm going to put a blank right here. You guys fill in what the probabilities are. All right, fill in those probabilities on our probability tree. Hopefully everyone's feeling good with that probability tree. It's making sense for you. Let's go ahead and multiply through. So we can just see, the probability of getting 1 and getting 2, probability of getting 1 and not getting 2, and so on. You can put in the probabilities. I'm going to put an equal sign right here. So are these independent? We already answered this one. No, they're not independent. What's the probability you get both contracts? We already have that shown there. So what is it?
0.16.
0.16. That's just the top one right here. So we're good with that because it says the probability of getting contract 1 and contract 2. I'll just put it right here. Now it would probably be better to write the full thing, probability of 1 and 2. And if this was a FRQ on the AP test, we'd want to write that in a sentence, but that's neither here nor there. All right. What's the probability you get no contract?
.14.
0.14. So the probability of not 1 and not 2 is 0.14. Very good. So we're looking at that for that answer. let X be the number of contracts you can get. What are the outcomes for this if we're going to come up with a probability model? What's the maximum number of contracts we could get, or this company could get?
Both.
Get 2. Minimum is
0.
0. And of course, we could get that middle ground, just get 1 contract. So we already found the probability of 0 and for 2. So I can just write those in. 0.16 right here, 0.14. The probability of 1 is either one of these conditions right here. So we can just add those together or just get the complement of what we already have. So your call on that. I believe 0.7 is the probability for that. Okay, so at this point, you have all the information you need. We created the probability model. That's part D. So now we just need to do part E. Find the expected value in the standard deviation. Calculator does all this work for us. I will just put your spots to put your answer right here. So you can kind of see the full process there, and that's kind of tying everything together from probability that we did before and now random variables getting tied into it with tree diagrams. So luckily you can see the calculator does a lot of this heavy lifting for us. And again, if you want to come back and look through this problem, I was going to move forward, but I can pause if there are any questions right now. And you can just respond in chat if you want, but those of you who are having trouble with getting the numbers to come out right, I don't know if you want to chat to see if the numbers are coming out right at this point. All right, there's one more that we're going to go through, and maybe for the sake of time, because we're already at 2 o'clock, maybe we can just run through this pretty quickly. In a litter of 7 kittens, 3 are female. You pick 2 kittens at random, create a probability model for the number of male kittens you get. All right, I'm going to do this without a tree diagram or anything. So we already know what the outcomes are going to be. All right, we could get, since it's 2 kittens and we're looking for the number of males, well, I know I'm going to get either 0, 1, or 2. And I'm spacing this out because I'm going to be doing my probabilities in notation form. And I'm going to give this a little bit, I'm going to give myself another one right here so we can actually do our numbers. So the probability of getting a 0, that would be, again, I'm going to kind of go through it quickly, but hopefully you're kind of already thinking in your head about how to get this. So it's going to be the probability of getting a female and a female. This is where you might not have this in your head, given that you already got a female to begin with. The probability of getting 2 males is the probability of getting, here's what I want to do actually, before I write this, because I'm going to need more room in the middle. You can probably tell. I'm going to scoot this line over a bit. Okay, this is going to be the probability of a male and a male given that you got a male the first time. So 1 is where it gets a little bit trickier because we only want to get 1 male. So I could get a male the first time, which would be the probability of getting a male and getting a female given that I got a male the first time. Or, and I could put this all into one big probability, but just to keep it simpler, I'm going to say we have 2 different probabilities that are mutually exclusive and we'll add them together. And then I could do the probability of getting a female first and getting a male given that I had a female the first time. And let's see, there were 3 females to begin with. So if I go left to right, when I first pick and I pick up a female, there's a 3 in 7 probability it's female. It is female. Now I can call it she is female. Okay. When I do it the second time around, there's 1 less female. So it's going to be what? This is where you guys can jump back in.
Uh, 2 out of 6.
There it is. 1 less female, 1 less kitten to pick from. Why would anyone want to pick 2 cats to have as pets? That seems excessive. All right, let's jump to the last one. You guys can do that math and figure out what the probability is. I'll just put an equal right there. Now we could, if there's 3 female, there's 4 males. So we're gonna do this. So again, if there's 1 less the second time around, it's a 3 in 6 probability. And you guys can figure out what that is. The middle one is where it gets a little bit, not more difficult. It's just we have 2 of them to do. So I could get a male the first time. That's going to be 4 out of 7. And then a female, there's only 3 females out of now 6 cats. I didn't get the female the first time, so there's a full amount. Or it's going to be female the first time. That would be 3 out of 7. And then maybe a male the second time around, which would be 4 out of 6, because there's still 4 males to pick from. So if I do that, we can just plug those numbers in real quick. And if you already have your probabilities, just write them in. It can be decimal. Okay, and I don't think we need to go through the rest of this problem. So the hard part, of course, is part A, or at least I think the hard part is part A. And the rest of it is done with the calculator. We don't need to answer that as a class. It's just more of the same. Plug that probability distribution in, which is going to be those 3 numbers. Plug your outcomes in, and then do your 1 variable stats, and you come up with your answer to that. So that's all good. I know we talked a lot about transforming data, and that is going to be something that we have to still spend some more time on Monday to help clarify that a little more. So I will clear this. Here's your homework. You can see right there, and it's I can't remember if there's others right here, but this is 25 and 27. When you get to those, when you check your answers, it might not match up. Just approach those today based on the way that we were thinking about it, but there's actually a little bit more to it. All right, so if that's not vague and nebulous enough for you. Again, at this point, if you have questions, stick around. If you don't, you can have a wonderful weekend, and I will see you on Monday.